the universal gravitational constant. Now, these values are not very readily available for most of you unless you remember them. But look at this, GRE squared, where the G is the value of acceleration due to gravity on the surface of the Earth, which we can take as 9.8. Although it doesn't remain a constant, we can take an average value of small g as 9.8 meter per second squared. And RA is the radius of the Earth, which everybody must have a fair idea what it is. So an average value of g on the surface of the Earth can be obtained by using the known values of mass of the Earth and the radius of the Earth. You can actually do that. The mass of the Earth is 5.98 times 10 to the 24 kilogram. And the radius of the Earth, I would like you to remember this value, 6.38 times 10 to the 6 meter. That is the radius of the Earth. But the average value, we know the radius slightly differs at the equator and at the poles. This is an average value. And using these two values, we can calculate a value for acceleration due to gravity. The value of the universal gravitational constant is 6.67 times 10 to the negative 11. What's the unit there? Newton meter squared per kilogram squared. And this is the mass of the Earth. And this is the average radius of the Earth. And that gives you our famous value 9.8 meter per second squared. So this is the average value of acceleration due to gravity on the surface of the Earth. So this g can be replaced by 9.8 meter per second squared. The radius of the Earth is 6.38 times 10 to the 6. So wherever we need big G times the mass of the Earth, we can replace that by small g times RE squared. I will ask you that a little later, so don't forget that. What happens to the value of G as you go higher and higher? The value of G at an altitude h. The value of G will change as the object is taken away from the surface of the Earth. At an altitude h, when the object is at an altitude h, the distance between the object and the center of the Earth will be RE plus h. Is that right? So we will replace the radius of the Earth now with the radius plus the altitude. So the value of G at an altitude h will be the universal gravitational constant times mass of the Earth divided by RE plus h all squared. Let's find the value of g, the acceleration due to gravity, at a height 200 kilometers from the surface of the Earth. Well, we know the mass of the Earth from the previous problem. We know the radius of the Earth. H is now given as 200 kilometers. And we know the value of the gravitational constant. Let's put all those things there. 6.67 times 10 to the negative 11 times mass of the Earth divided by radius of the Earth plus the altitude at 200 kilometers is 0.2 times 10 to the 6 meters. Alright, can you use your calculator to work out what this is? That will give you 9.2 meter per second squared. So if you go to a height of 200 kilometer, the value of acceleration due to gravity will decrease to 9.2 meter per second squared. That means the weight of the object will be less at that altitude. Is that right? That's correct. Let's now talk about gravitational field. What is a field? Now, this is a concept we will talk about again in physics too. Whenever we talk about a force, we use the concept of a field to describe it. Now, suppose an African chief says, what you see within this fence is my field. What does that mean? That is my field. What he means is, this is where I exert my authority. Now, you can use the same meaning to describe a gravitational field. Earth has a gravitational field. In other words, the space surrounding the Earth where the Earth will exert a force on other objects is the gravitational field of the Earth. So, gravitational field of an object is a three-dimensional space around that object where that object will exert force on other objects. That is the definition of a force field. The statement of the law of gravitation implies that an object placed outside the Earth's surface will experience a force towards the Earth. Now, this is true no matter where the object is placed. No matter where the object is placed, if the object is on the surface of the Earth, it will experience a force towards the Earth. If the object is taken to an altitude h, it will experience a force towards the Earth. No matter where you place the object, it will experience a force towards the Earth. That means the three-dimensional space surrounding the Earth where it will exert a force on other objects is the gravitational field of the Earth. This is equivalent to saying that there is a gravitational force field around the Earth. Now, here is the Earth. I have used arrows to represent this. If I keep an object here, it will fall towards the Earth. If I keep an object here, it will fall towards the Earth. If I keep an object over here, it will fall towards the Earth. That means the space surrounding the Earth where the Earth exerts a force on other objects is the gravitational field of the Earth. Now, why have I used the arrows pointing towards the Earth to represent that field? I have used arrows to show that the direction of that force is directed towards the Earth. That means the field is a vector quantity. The field has a magnitude and a direction. What is the magnitude? Magnitude is the amount of force an object will experience, and the direction is towards the Earth. You see, a field is a vector. It has a magnitude and a direction. All right. The gravitational force field is a vector quantity that has a magnitude and direction. The direction is towards the center of the Earth, as is indicated by these arrows. The magnitude or strength of the force field. How do you know what the strength of the force field? Now, where is the strength of the field greater? If you look at these lines that represent the force field, where are they closer together? Now look at my marker moving. Now, along this circle, the lines that represent the field are closer together than along this circle. That means the strength of the field is stronger. The field is stronger closer to the Earth than when you go far away. The strength of the field is greater at points that are close to the surface of the Earth. If you move away from the surface of the Earth, the strength of the force field will become weaker. So the distance between these field lines, these lines can be called field lines. The distance between the field lines indicates how strong or how weak the force field is. Well, there is a definition for the strength or the magnitude of the gravitational field at a point. It's a standard definition. Now I want you to learn this. The strength of the gravitational force field at a point is defined as the force per unit mass placed at that point. So if I have a mass of 1 kilogram, suppose this ball has a mass of 1 kilogram, it has approximately 1 kilogram. If I can now measure the force on this basketball placed at this point, that will be a measure of the strength of the gravitational field at this point. If I take this basketball to an altitude of 1 kilometer and measure the force on this 1 kilogram, that will be a measure of the gravitational force at that point. So in order to measure the strength of the gravitational force at a given point, you place a unit mass of 1 kilogram and measure the force it experiences, and that will be a measure of the gravitational force. The strength of the gravitational field at a point is defined as the force per unit mass placed at that point. What is the unit for gravitational field? It is force per unit mass, Newton per meter. Let's write that down and see what that is. The unit of the gravitational field is Newton per meter. Now, do you know what a Newton is? A Newton is a kilogram meter per second squared. Is that right? Alright, now let me make one correction what I have been saying, which is the strength of the gravitational field is the force per unit mass. Force per unit mass. What is the unit for that? Newton per kilogram, not Newton per meter, as I said earlier. So make that correction, please. The strength of the gravitational field is force per unit mass. It must be Newton per kilogram. So it must be Newton per kilogram. And if you remember what a Newton is kilogram meter per second squared. And if you divide that by kilogram, you notice kilogram and kilogram will cancel. That gives you the unit of the gravitational field is a meter per second squared. The unit of gravitational field is meter per second squared. But aren't you familiar with another quantity that is measured in meter per second squared? Acceleration. Yes. So let's see how this is related.